Okay, good afternoon. Welcome back. Today we'll be going through the third lecture in CE 530. Today what we're going to do is we are going to pick up where we left off last time talking about cement, and we are going to start going through cement and the hydration process. And you'll notice on the first slide that we've got today, this is a slide that I was actually sent by a student last semester looking at this. I think it's kind of an interesting slide for a few different reasons. Obviously you can see it as a sort of joke, sort of advertisement where the rate of hydration is incredibly important. But one of the things that I find incredibly interesting is the caption. You'll notice that it doesn't say fast hydrating cement. It says fast drying cement. Drying and hydration are two completely different things, which we will hopefully understand by the end of this lecture, so that if any of you are ever out there marketing a new material, you'll try to use the proper terminology. All right. Obviously, for those of you who aren't familiar, this is sort of a spoof picture. All right, this is something that is not going to be something that you could expect. All right, it typically takes slightly longer time period for the concrete to start to develop strength and become solid. What I want to do is I want to start off with a review of what we were talking about last time. And what were we talking about last time? Making cement. All right, so we talked about some of the major components of making cement. We basically said that we're going to start off and we were going to be quarrying raw materials. And the raw materials that we're most interested in are?
Limestone.
All right, limestone, clay, shale. All right, we need to get a calcium carbonate source. We need to get some other properties into the system. We are going to crush those materials, and we're going to crush them down to a relatively fine set of aggregate, maybe something smaller than about 20 millimeters. And the reason we want to crush this down to be relatively fine is because we want to try to get something that is homogeneous. We want something that's relatively uniform. All right, so the material will then typically go through the raw feed mill. All right, it will continue to be homogenized, and then it will start to go through a process of heating. And we mentioned that all of this heating may not happen inside the kiln because we are going to use preheaters and precalciners. The preheaters and precalciners are there to mainly recover waste heat. All right, so during the first part of the process, we are going to be driving off water. During the second part of the process, we are going to be driving off the CO2. It will then go through the remaining portion of the kiln. While it's in the kiln, we are melting about how much of the overall material?
20%.
25%, something like that. And we are transforming the material into a material that's going to be much more reactive. Once it comes out, we are going to cool it down by blowing air across it. We're then going to take the material, we're going to add gypsum or some sulfate source into it, send it through a grinding mill, and hopefully no one tried to put the golf balls into the dryer. I haven't heard anyone screaming about that. All right, but basically the idea is we're going to drop steel balls onto the clinker to make it a fine powder, and then we have an overall cement product that we are ready to start using. All right, let's talk a little bit about the composition of the cement. All right, and then we'll start to talk a little bit more about how this material starts to develop strength. All right, as we mentioned, if we were to look at sort of the ingredients list, you were to flip the bag of cement over like you flip over nachos or you flip over some other food product, and you start reading what the ingredients are that went into it. All right, you'll see that there's lime, silica, ferric oxide, alumina, all right, carbon dioxide, and as we mentioned before, if we actually write them out with the oxide notation, the chemical equations that we would use would tend to get relatively long. So cement chemists have used a relatively shorthand version of the overall technique, and what they're going to do is they're going to simply make lime C, all right, silica will be S, all right, alumina A, and this is the notation that we're going to use throughout the rest of the class. The other thing that we'll talk a little bit about is you can look here at the last column, which are the weight proportions of each of those materials, and you get a relative idea of what's going into each bag of cement that's being produced. All right, if we were to take this cement and we were to put it into an epoxy, we could actually look at it in something like a scanning electron microscope. And here you can see a picture of the cement particles in an epoxy matrix, and they've been imaged in a scanning electron microscope. Basically, the color here is giving us a little bit of an indication of the density of the overall material when we're looking at it in this particular mode. The dark spots are where there's epoxy. The brighter spots are where we have something, some of the crushed up clinker. Now if we stop there, we would basically just be able to get a little bit of information about the size and the shape of the particles, maybe a little bit about the density of the particles, but we can actually do something called energy dispersive X-ray spectroscopy. All right, and this will basically give you the chemistry of the overall system. So you can look at, you can basically get a signature, or you can sort of get what types of materials, what chemicals are at each point inside of the overall picture. So here, anything that is calcium is showing up as blue. Right? We can not only do this for calcium, but we can do this for quite a few of the other materials. Right? And what you can see is calcium is obviously that bright blue one that we were looking at. We could look at potassium, we could look at our sulfate source, we could look at our silica source, and you can now see inside of that image, right, where this chemical is going to be most predominant. Right? So we can see here that there is some silica. All right in this particular region. You can see regions where the potassium is very high. All right, and now we can start to put those images together and start to try to convert those raw chemistries over into the compounds that we're typically going to be talking about for our hydration reactions. Right, so we're not necessarily interested in the pure chemical there or the oxide that's there, but we're really interested in the composition of the overall material that's there. And we're going to look at 4 main compositions. Right? The top 2 are the ones that are really the most important to us, and you'll remember I referred to these as the calcium silicates. Right? Tricalcium silicate, which will be C3S, and C2S, which is dicalcium silicate. Right? That is really the business portion of the cement. That's the portion that's making up the majority of the cement. That's about 75% of the overall system. All right, you'll see there's also tricalcium aluminate, C3A, in the system. All right, and then we have the ferrite phase, which is making up a smaller percentage of the system, and then gypsum that we want to add into the system, or the sulfate source, all right, that goes in the grinding process. Now, how do you get from knowing the chemistry of the raw materials to getting to these chemical compounds or these chemical compositions? Use something called the Bogue equations. And in this class, I'm not going to go through the history of the Bogue equations and where they come from. The Bogue equations are listed in your textbook if you ever need to do this set of calculations. All right. However, I will say that in cement chemistry, they will spend a long time going through this because they will derive where this comes from on the phase diagram. For the sake of this class, you can assume that Bogue knew what he was doing. All right, you can go through and apply his set of equations. All right, and there are 2 different sets of equations depending upon the chemistry of the system that you're looking at. And what that will enable you to do is it'll enable you to go from the chemistry of the system into the cement compositions that we have listed on this particular page. Right? As I mentioned before, what we're really interested in are the calcium silicates, which are going to make up about 75% of the system. Right? And then we're going to spend a little bit more time talking about the aluminate phase. All right? One of the things that you will notice is every time we start to talk about these percentages, and I put the percentages up on the screen, they aren't going to total up to 100%, because there are a lot of other trace materials that are inside of cement, because this is a material that is being mined out of the earth. We're doing it very rapidly, so things aren't pure. There are going to be other things in the system. Right? I'm going to focus in for this class on the main compounds, all right, that we're looking at, on the main portions of the overall chemistry. Now, you'll remember we went back to that picture that I had showed earlier of the cement being imaged in the SEM. Here is a similar picture of that, taking the information that we got from the chemistry, using something that's very similar to what Bogue does, but it's a little bit more sophisticated process that NIST has adopted to do this. And they've now defined the cement in terms of these different compounds. Right? So what you will notice is that there are different colors in this system. The red would be something like your C3S. Right? And one of the things that I want to start to point out is if you start to look at the particles, you will notice that there aren't a lot of particles that are simply C2S or C3S. You'll notice that there are particles such as this one. Now I've got red, which is a fantastic color to be using here. So let me switch over and change the color of the... for this slide, we'll use something like a yellow. All right, I'll circle this particular region up here on the cement particle. What you will notice is that there are regions that are a dark red, and there are regions that are the lighter pinkish color. The lighter pinkish color will be your C2S. The darker red will be your C3S. And one of the things that's important to notice here is you have a lot of these particles that are made up of more than one of these particular compounds. So they will be coexisting. Right? And this is an important understanding because it's not like we've got C2S particles and C3S particles, all right? But we have all of these inside of the overall system. Right? So we'll change our color back. All right. One other thing I want to talk about, in addition to a little bit that we've touched on the chemistry, I want to talk a little bit about the issue of fineness. Right? We said that grinding was the last step in the overall process, and there are really sort of two measures that can be done to get an indication of the fineness. One of them is determining the surface area, and this is typically done by passing air over the system, and you can determine the surface area of the particles. The second one is to determine the size of the particles through doing something like a particle size distribution. Now, obviously, the surface area is going to be related to the particle sizes, and why would we be so interested about the amount of surface area, the size of the particles? All right, it's going to start to control the rate of hydration or the speed of the reaction. The more surface area there is on the particles, all right, the more that these particles can start coming in contact with the pore solution or the water, and they're going to react faster. Right? So one of the things that we really want to keep in mind is, in addition to the chemistry of the system, the surface area or the fineness of the cement paste is going to, or cement powder is going to be incredibly important. So we'll see typical. I've listed a couple typical surface areas down toward the bottom. Something that might be a normal cement is listed here as 350 meters squared per kilogram. High early strength is going to be higher than that. It means it's going to react faster because it has more surface area. All right. So again, the key aspect of cement, the finer it is, typically the faster it's going to react because it has more surface area, and the reaction rate is going to be mainly a function of the amount of surface area that's present. So finer particles are going to react much faster than a coarser ground cement. Now you may say, well, why do we care so much about this? Does this ever become something that's practically important? Well, there are two real reasons why this is practically important. One of them is we can actually make different types of cement, all right, and they'll be distinguished based on their fineness. So we can start to look at people making cements that gain strength very rapidly, all right, which will be referred to as a type 3 cement because they typically are ground much finer. But one of the other things that the cement industry is facing is this graph that I've shown here, which has the sort of the age of the specimens listed on the x-axis. On the y-axis, you'll see the strength development, and you'll see the red line shows what the typical cement or the average cement was in 1950. The blue shows what the average cement is in 1990, and you'll see that cements have become more efficient over time. They gain strength faster. Well, what is one of the main ways that they're going to be gaining strength faster? They're going to be grinding the cement finer. Now, in addition to causing the reaction to occur faster, this has some other consequences that we should be aware of. The finer the cement, the more it's going to hold on to the water. So water is not going to bleed to the surface as quickly with a finer cement. All right? In addition, we are typically going to see increased amounts of shrinkage. Right? And we'll talk about this as we get toward the end of the semester, but finer cements will typically exhibit a little bit more shrinkage. Right? Sometimes we can see a reduction in durability, all right? And we can also see that there'll be an increased amount of gypsum needed to slow down that reaction at early ages. Right? A little bit about the mill certificate, but I'm not going to go through this in great detail. With each cement, the producers will provide you information on the cement that's being produced, and you will get a typical mill certificate. This happens to be a mill certificate that's been sent by one of our local producers, and during the course of this class we'll keep coming back to a sort of a typical or a reference cement. So the SEM images I showed you before are for a particular reference cement. We'll do some calculations and we'll do some simulations with Semhide 3D later on talking about a particular reference cement. This is that particular reference cement that we're using. So this is a mill certificate for that. One of the things that I will point out is that this is based on production averages. So it's typically averaged out over the course of a month. So if you're looking to trace down one particular truck or you're trying to trace down one particular piece of clinker, this isn't the way you're going to do it. All right, this is something that's looking at the production run or the production average over a relatively long period of time. It can, however, be useful for tracing changes. All right, so if all of a sudden you're a producer and you start noticing that your materials are responding differently or they're not setting up the way that you expect them, you're having problems with an air entrainer or a super plasticizer, one of the first things to really do is to be looking at these mill certificates to see if anything is changing. Is the fineness changing a lot? Is the chemistry changing a lot? This is becoming increasingly important in places where the clinker may not be produced locally. You'll remember last time we talked about the fact that once you get some of these materials, they can be shipped on water fairly inexpensively. And there are a lot of materials that will be produced in other countries and shipped into the U.S. What typically happens is the clinker is shipped into the U.S. and then there's a grinding terminal or a grinding facility where these powders will then be manufactured. Right? If you are pulling cements out of one of these grinding facilities, it's highly likely that that chemistry of that cement could be changing dramatically during the course of a product or during the course of a production run or the series of a summer, depending upon where that cement is coming from. So this gives you an indication of what the chemistry and what the compounds are for that system. You'll also want to, for records and quality control, you'll want to keep track of these to trace down what some of the problems may be a little bit later on. I'll zoom in a little bit to show you what's on these sheets. On one side, you'll see a lot of this chemical data. This is the type of information that we were showing before. This information is determined using ASTM C114, right, which is the ASTM to give you information on the chemical data. And then you'll see that a lot of the different materials that we've been talking about up to this point, silica dioxide, calcium oxide, are all shown here with their weight percentages. So it gives you the chemistry of the system. They'll also typically go through and do the Bogue calculation for you directly, which is shown right down here, so you can get an indication of the four main compounds that we were talking about earlier. Our calcium silicates, which are the top two, okay, and then our C3A and our C4AF. On the other side of the mill report, all right, you will see things that are typically a little bit more related to the physical properties of the cement, where you will typically see a measurement of the fineness. Here you'll notice that the units are a little bit different than the units that I had mentioned earlier. You'll see other things like the strength or the strength of cubes that are manufactured at different ages. That'll give you a little bit of an idea of the strength development. And then you'll see information about the set time. And we'll come back to this as we go later on in the semester to talk a little bit more about what set time means and what a VICAT test is and how we determine it. But it gives you a little bit of an indication of what are the properties of the cement that you're dealing with. Now what I want to do is Mike, question?
Yeah, on the grinding facilities, do they produce the mill certificate or the people who produce the clinker to the grinding facilities?
I believe you'll get it from the grinding facility, but I would have to double check on that. All right, I believe that when it comes, it'll have its own chemistry, but then the testing would actually be done at the grinding facility, but I need to double check on that, and I'll let you know the next time we meet. Okay? Other questions? All right, typically there'll be a quality control lab that's looking at doing those tests, but I'm not sure who's required to do it. Okay. Other questions? All right, let's jump a little bit into hydration. Obviously, one of the things that we're most interested in is how rapidly is our material going to react. All right, when we start talking about hydration is really synonymous with the phrase reaction. We're really looking at how fast the cement is reacting, and the reason we're typically interested is because our properties are going to develop relatively slowly over time. All right, you can see in this particular picture here, this is a fairly typical concrete at 20 degrees Celsius, about room temperature, and you can see the rate of strength that's developing as a function of time. By a week, you can see that we may be up to 75, 85% of the overall strength. But during the first few days, that strength development is fairly significant. Right, we're going to go from something that right around the time of set, maybe 5, 6 megapascals, all right, all the way up to something that's 50 or 60 megapascals. And typically, strength is one of the properties that we're interested in. Now, many times engineers are most interested in strength, but almost all of the properties that we're dealing with are going to be developing like this over time, whether it's elastic modulus, whether it's tensile strength, whether it's diffusivity, whether it's penetration resistance, right? All of these will be developing as a function of time. And the real reason that they're developing as a function of time is because the hydration process is taking place. So I've drawn you some beautiful cartoon illustrations of my vision of cement in water. And you can see here in the first picture, Roman numeral 1, we have the cement particles, which are shown here in white. We have the water that's added, which is shown here as the dark blue background. All right? And we can see basically that we would have the cement particles swimming in a sea of water. Well, after a short period of time, almost instantaneously, what we're going to start to see is the cement, all right, and at least the things on the surface of the cement are going to go into solution, and it's going to change the composition of the overall solution. So now we no longer have pure water. We have a pore solution, which is essentially water with things swimming in it. All right, we're going to have ions in the system. We're going to be changing the chemistry of the overall system. We're also going to see that there's going to be some reaction taking place at the surface of the cement particles. Right? And there will also be cases where reactions will take place sort of in free space. All right? In the free space there. They're most likely to start at surfaces because there's the lowest energy for the reaction to start taking place at the surface. Now, as this reaction proceeds, what you're going to see is the cement particles are going to be getting bigger because the hydration rim will be increasing even though we're using up the cement. Right? So the white part on this diagram is going to be getting smaller. The outer edge, this gray part, is going to be developing, and this is the hydrated product. This is that glue, and that glue is going to be a portion of the white cement, all right, that's shown here, the white colored cement that's reacting with the pore solution and creating this new volume. At some point, these particles are going to start interacting with each other. They're going to start sticking together, and that's typically what we refer to as set. And this is going to define when the material goes from really a fluid system into a solid system. Over time, this is going to continue to go on. This reaction is going to continue to go on. And you're going to see this system filling in more. You're going to see this open space being reduced. And the bonds are going to be developing more and more between those particles. As we get more and more hydration product forming, as we get more and more glue, as we get more and more new solid, the strength of the material is going to go up, and it's going to be harder for things to go through the system. It's going to be harder for ions to diffuse through the system, so the diffusivity will go down. The chloride penetrability will go down. All right? The strength will go up because there's more solid in the overall system. Right? I want to talk about a few different ways that you could measure the extent of this hydration that's taking place. All right, and I will talk about 3 methods. These are 3 of the sort of predominant methods that are being used, but there are other methods that are out there. 1 will be based on the exothermic reaction. Right? 2 will be based on sort of the percent of material that's been transformed, the amount of cement or the amount of water that's been used up. And 3 will be based on the fact that the overall volume of the system changes. All right, due to the reaction. So we'll sort of go through these. Now, each one of these should give you complementary information. Each one of these should be able to tell you how much of the hydration reaction is taking place. All right, so the first one we'll talk about the fact that cement, all right, when it reacts, undergoes an exothermic reaction. All right, so this is a reaction that is going to release heat. It's going to give off heat. So if you were to take a bunch of cement, mix it up with water, and stick your hand on that, you will notice that over time, that concrete is going to start to get hotter. Right? And this is something that we need to deal with, and we'll talk about later on from a very practical sense from field applications. Right? You could also cook an egg on the concrete if you really wanted to. It's going to give off a substantial amount of heat. And if we measure the amount of heat that's given off, that gives us a way to quantify the extent of reaction that's taken place. All right? So we could put this into a calorimeter. All right, and there are different types of calorimeters, but it's basically a way for us to measure the heat or the energy that's given off. And if we know how much energy is given off, we know how much of the reaction has taken place. All right, so it gives us a simple, non-destructive way of starting to look at this. Now, I can relate this back to something that you may have had some experience with. And if we were able to have food and drink into the room, I would distribute now to each of you a synonym for the cement that we're going to use, all right? A direct replacement for the cement that we're going to use. And it is the fabulous atomic fireball, all right? You could go and you can go online and you can find out how fireballs are actually made, all right? And what you'll find out, it's kind of interesting. They start off with a single grain of sugar and they build up the system around it, all right? But if you look at the fireball and you use your mouth as a calorimeter, as a measure of heat, all right, you can make some interesting observations. You will notice that initially the fireball causes a sweet taste inside of your mouth. There's a coating of sugar on the surface of the fireball. This is very similar to the alkalis and other things that are on the cement particles going into the pore solution. Now, I am not saying that pore solution would taste sweet if you were to drink it. Please do not try that. All right. However, it's a very similar type of analogy that can be made. After a little bit of time, though, that sweetness is going to go away, and the exothermic reaction is going to begin. The fireball will begin getting warm inside of your mouth. Right? This is the cinnamon going into solution that's inside of the fireball. In the cement case, this is more and more reaction taking place. Right? Heat being liberated by that reaction. Right? During this time, the fireball is going to progressively get smaller. As the cement particle reacts, it will progressively get smaller, but the hydrated products around it will cause these particles to start to grow together until you get to a point, especially in the cement system, that the surface reaction starts to give way to something that's more like a diffusion controlled reaction. Now, we can plot this experience out for a cement, right? And we could plot either the total heat that's given off, or we could plot the rate of heat that's given off. And the most common way to see this data is the rate of heat. All right, so this is the derivative of the heat that's given off with respect to time. All right, so this would tell you what the rate of reaction is. All right, remember that the heat that's given off is directly proportional to the extent of reaction. Here we can see if we have the rate of heat the rate that heat is given off being measured, we have an indication of the rate of the reaction. And you will notice that there are really 5 stages of the overall reaction. Rapid heat evolution, this happens typically during the first 5, 10, 15 minutes. Right? This happens very, very quickly. Stage 2 is the stage that really makes it possible for us to use concrete in the field. It's the dormant stage. All right? It is where the concrete seems like it goes to sleep. The reaction is not zero. The rate of reaction is not zero in this region, but it's very, very low. It's very close to zero. All right? The concrete is essentially sleeping. This will happen typically 2, 4, 5 hours, something during this period, until we get to region 3. And region 3 is where all of a sudden there's going to be a rapid release of heat, a rapid amount of reaction that's taking place, and we are typically going to refer to this as the acceleration stage. Right? This will take place for 4, 8, 12 hours, something like that. The rate of heat will start to decrease when the diffusion-controlled reaction starts to take place. We'll go into stage 4, and then we'll get into a point where we're really at steady state, where the reaction is still proceeding, but it's proceeding very, very slow, and this will be something from a few days out to many, many, many years. Right? The reaction will continue as long as there is water in the system and there's cement that needs to be used up. It will just be going at a very, very slow rate. Right? The second method is to really look at the amount of material that's been being used up, the degree of hydration, the extent of material that's been reacting in the overall system. So here you can either examine the amount of cement that's being used up, or you can measure the amount of water that's being used up in the reaction. All right? And people do it both ways. All right? You will hear people, basically the idea here, all right, would be if we started off with an overall material, which is this grayish colored circle, so this is our original material. right? Over time, that material is going to react or going to transform or going to do something else. So as a function of time, that material is going to react, and that material is going to begin to transform from our original gray material into this new red material until a point where we've gone from 0% of the material being red to 100% of the material being reacted. Now, I've shown you this graph that doesn't really come from a cements lecture. It comes from a metals lecture. Right? Same type of behavior going on. We are going to see a reaction taking place. We're going to see the gray material being used up, being reacted and coming something else. And we're going to go from a 0% reaction on the bottom, or 0% of the phase that's being transformed in a metal, to something where we've got almost 100% of the material being reacted or transformed. When we talk about degree of hydration, this is what we're talking about. We're talking about how much of the cement has reacted, or how much of the water has reacted in the overall system. We're measuring the extent of the material that's been used up. Right? I won't go into a lot of detail, but we will come back to this. There are several different people who've developed these types of equations that describe this simple type of reaction kinetics, because it happens for a lot of different materials. One of the things that's very interesting is it's typically referred to as a KJMA model, and each one of these people came at it from a very different field and a very different perspective, but the equation worked out to be very similar. One was a chemist, one was a metallurgist, one was a mathematician, and all of these people started to look at the growth or the extent of reaction that was taking place, and they used sort of that exponential type of equation to describe this S-shaped transformational process where we go from 0% of the material reacted to 100% of the material being reacted. Turns out that in its conventional sense, the KJMA doesn't work really well for cements. It either fits at the beginning or it fits at the later side, and it's because the reaction changes for us as we go throughout time. But I don't want to spend a whole lot of time talking about that. Conceptually, we start out with cement. All right, that cement here, it's shown in black. That cement is in water. That cement is going to react, and we're going to form hydrated products. At some point, those hydrated products are going to start to interact with one another. We're going to get a solid material. This occurs if we have a very high water to cement ratio. We have leftover space that's filled with water. If we have a very low water to cement ratio material, we're going to use up all the water and we're going to be left with leftover cement. Right? One way that this could be measured is by measuring the non-evaporable water that's in the system. All right, so very simply, there are two types of water when you look inside of a cement. All right, there is water that can evaporate, and this is water that's typically lost up to 100 degrees, 105 degrees Celsius. And there is water that is non-evaporable, and this is water that has chemically combined. Water that's chemically combined is part of the hydration process, so this is water that's been consumed to react with the cement. All right, so before we were saying, well, we could measure the extent of the material that's reacted. Here you're measuring the amount of water that's reacted. So in order to determine this, you would basically take the weight of water that's lost between 105 and 1,000 degrees, and that would tell you something about the amount of water that's reacted in the system. And when we start to talk about non-evaporable water, this is typically what we're talking about, a way or a measure to get how much of the water has reacted in the system, how much of the cement has reacted in the overall system. All right, the other way that this could be done, all right, and I seem to have lost it. All right, the other way that this could be done is using a SEM image. All right, so you could use like a scanning electron microscope image, and you can look at how much of that cement has been used up as a function of time. So this would be very similar to the types of cartoons I showed earlier, where we were talking about setting with the white cement particles being inside of the blue. You could measure how much of the surface area of white is reducing over time, and that tells you how much of the white material or the cement has been used up as a function of time. All right. Questions on this? Concerns? No jokes. We never joke with cement, I guess. All right. One of the things is each of the compounds is going to react at a very different rate. All right, now here we are plotting this as a function of degree of hydration, so we're simply talking about how much of that compound has reacted. We're not making any judgments about its strength. We're not making any judgments about its quality. We're just saying how much of this particular material has reacted. All right, degree of hydration is how much has reacted. You will notice that the C3A is a speedy little fellow. All right, the C3A reacts very, very quickly. The C3S is going to be slower, and the C2S is the slowest of all three. All right, the C3A is so fast, all right, that we would have problems actually placing it in the field. All right, we actually have to slow that reaction down, and in order to do that, that's why we're adding the gypsum or the sulfate source, is to slow this down so that the dormant period is long enough that we can actually work with the concrete in the field. Right? That's why we're adding the gypsum in the overall system. So the dashed line here shows the C3A. The solid line shows the C3A plus the gypsum, which from a practical point of view is really much more of what we're interested in. Gives us time for the system to get out, get placed, and we can start working with it. Right? Here is some strength development. Another way that you could measure this, here's some strength development as a function of degree of hydration. This is measured by non-evaporable water. And you can see in a paste, the system is very linear. We will come back to this later on in the semester because one of the really important things that I want to draw your attention to is this is for a paste. All right? You can measure the extent of reaction using something like strength or other types of properties when you're measuring it on a single system of paste. When we start to talk about concrete, this will get much trickier. As I mentioned before, we weren't making any quality judgments based on when we were talking about degree of hydration. Now this graph starts to say, well, they may react at different rates, but just because they're reacting doesn't mean they're going to have the same strength. All right, so here what we've done is we've plotted the strength development for each of these materials as a function of time. And a slightly different picture starts to emerge. You'll notice the C3A and gypsum down here toward the bottom. You'll notice that it reacts very quickly, but then it really flattens off. All right, so it reacts very fast, but it's not very strong in the long run. All right, our C3S and our C2S, all right, will take a little bit longer to react, but they are going to get to much higher strengths, and eventually the C2S and the C3S will start to converge on roughly the same strength. All right, it's just the C2S takes a lot longer for it to get there. Okay, so the main difference, C3S and C2S are going to be much stronger. The C3A reacts faster. Okay. Final thing I'll talk about is the third method, all right, is really looking at a volume change in the overall system, all right, and this is commonly referred to as chemical shrinkage. Chemical shrinkage is simply the fact that if you start off with a bucket of cement and a bucket of water and you mix them together and they react, you get 1.9 buckets. All right, a tenth of a bucket goes missing. All right, there is a volume reduction that takes place because of the reaction. Right. Now this has been observed, this is for over 100 years this has been known. Le Chatelier observed this and saw that there was a reduction in the volume of cement paste when it reacted. All right. Powers used this as an indirect measure of the index of the progress of a reaction that was taking place. Other people have related this to strength development. There are some new test methods that are out there because this is a relatively easy thing to be measuring. This is a description of the chemical shrinkage test that's used in ASTM. The basic idea here is cement will be placed at the bottom of a jar. You'll place water on top of it, and you'll measure the amount that the water goes down over time. The volume reduction as a function of time. Right? Water's not being lost here due to evaporation. It's being lost because as this system reacts, it gets smaller, and the volume is being measured. Right? You could also do this in an automated fashion, and here I'll show you a little bit of a picture. This is a cement paste, all right, that's being suspended from a balance. All right, the basic idea is the cement will become more dense as it reduces in volume, and you can measure the change in buoyancy of the system. All right, here's a little bit picture of it that's a little bit closer. All right, where you've got the cement paste at the bottom. It's going to have a thickness of water on the top, and then the whole thing is going to be placed in paraffin oil. And if you plot this as a function of time, you will notice that this is the chemical shrinkage or volume reduction in terms of the volume per gram of cement. So we're measuring how much the system has shrunk over time. All right, and it's plotted as a function of time. And this is the total volume change that's taken place. All right, if we wanted to look at this and compare it to, let's say, the heat of hydration data that we saw before, all right, we could take the derivative of that, and that would tell us about the rate at which the reaction is occurring. So hopefully you will look at this graph and at least start to think that this might be similar to the heat of hydration graph that I showed you before, where you see a rapid initial volume change very early on for the first 10 or 15 minutes. You see a dormant period that's phase 2 here. You see the acceleration period where there's a lot of shrinkage taking place, a lot of volume change, and then you see a slowing down process as a function of time. Same type of information obtained from a very different type of test. One is measuring the heat that's given off, which is an index of the reaction. One is measuring the volume change, which is an index of the reaction that's taking place. All right? The final thing that we'll talk about today is we'll get a little bit into some of the chemistry of the reaction that's taking place. Okay? The two main types of reactions that we're going to be talking about, again, we're going to focus in on the calcium silicates. Right? And we're going to talk about the calcium aluminate phase. Right? We're going to focus mainly on these. Now, there are a lot of other things that are going to be happening in the system. We're not going to focus on them because of time. Right? The other thing that I will mention is we are assuming that each of these reactions will be relatively independent of what else is happening in the overall system. Right? And that may not be the exact case when you actually get into the actual system, but for the discussions that we're going to have, we're going to assume that they're independent of other reactions that are taking place. Right? What you'll notice with the calcium silicates, all right, you'll notice that our calcium silicates are going to combine with water, and they are going to form two things. They're going to form a calcium silicate hydrate, all right, our CSH, and they're going to form a calcium hydroxide. Right? If you want to think of these in sort of a yellow brick road type of idea here, right? We all have seen the yellow brick road, Wizard of Oz type of thing. You remember that there were two types of witches. There were good witches and there were bad witches. Right? There are two types of products that are forming here. There is a good glue, which is the CSH. All right, that we're after. Calcium hydroxide is sort of the byproduct, and it sort of leads us to some of the problems that we have in some of our cements. So the CSH is really what we're after. This is going to give the strength. This is really what we're after. The calcium hydroxide is a byproduct that's going to come out of this. You will notice that there are different amounts of calcium hydroxide produced, whether it's C3S reacting or C2S reacting. C3S has a lot more calcium hydroxide being produced, and this we will come back to when we start talking about supplementary materials. Right, when we start to talk about fly ashes and slags and things like that. All right, our tricalcium aluminates, our C3A is going to react with our gypsum and is going to react with water. Now, one of the things that you will notice here is you can look at all of the numeric coefficients and you'll see 2s and 3s. Right? This number here is an impressive number. It's not 2.6, it's 26. Right? There's an enormous amount of water that's going to go into the system, and that's going to typically be producing our ettringite. Okay? So our C3A is going to react with the gypsum, and it's going to bind up an awful lot of water. Right? If we look at this curve and we start to look at what's happening with our calcium silicates, again, rapid heat evolution during the first 15 minutes. All right, very rapid reaction taking place on the surface. Calcium and hydroxyl ions are going to be released from the surface. Right? We'll also have alkalis leaving the surface going into solution. We will see a rapid rise in the pH. All right. The size of the cement isn't going to be changing much. It's not like it's going to go from a 100 micron diameter down to a 40 micron diameter. We're just talking about just the very surface is reacting in the overall system. Right? It'll then remain in the plastic state for about 1 to 4 hours. We'll continue to have some dissolution. Calcium hydroxide will be going into the solution until they really reach a critical value. And typically it's believed that this period ends when the calcium hydroxide begins to crystallize inside of the overall system. All right. Once we start to see calcium hydroxide precipitating out of the system, that's typically a signal that we're at the end of phase 2, we're at the end of the dormant period. All right. This is sort of going to determine a trigger, or we're going to start to initiate the rapid reaction that's going to take place. So we're going to start to see a rapid reaction that takes place right before the concrete begins to set, right before it starts to set up. Right? Now this dormant phase is incredibly important for the transport of concrete into the field. Right? During the acceleration phase, right, we're typically seeing a large part of this reaction that's taking place that we mentioned before. Right? We're going to typically see a CSH barrier forming around the edges of the cement particles. We're also going to start to see calcium hydroxide precipitating out of the solution, as I mentioned before. And here the calcium hydroxide is going to form preferentially on other surfaces. All right? It's going to be easier for the calcium hydroxide to precipitate out and form on a sand particle or something like that because the surface will reduce the overall energy for the reaction to proceed. So one of the things that you will start to notice, all right, when we start to look at the structure of the actual cement paste, is there's a lot of calcium hydroxide that tends to be right on the edge of a sand particle or an aggregate particle, and this is one of the reasons why. The deceleration period will start, all right, it'll start to decelerate because now all of a sudden for that water to react, it has to go through the CSH, get to the unreacted cement, and then the reaction has to take place. It takes longer and longer for this to happen, the thicker that overall shell starts to get. And then we get into a steady state period. I can give you a little summary of the reactions. We'll go through this in much more detail later on when we start to talk more about hydration. But these are the 5 stages that we were talking about, and then the relevance that I tried to mention here, where we start to talk about initial set, we start to talk about final set strength gain, and then later strength. All right, again, the C3S, all right, ions are going to be released from the surface. We're going to get a protective barrier. At some point, calcium hydroxide is going to start to precipitate out of the system. When that happens, we're going to see this rapid rise in heat. We're going to see rapid reaction taking place. The cement is going to continue to get smaller and smaller. We'll get a diffusion-controlled reaction that takes place for the remainder of the reaction process. Right. At this point, I'll jump ahead a little bit. I won't go into great detail right now about the tricalcium aluminates. We will come back to that later on in the semester. But the basic idea, you're going to have a very similar type of curve. All right. Very similar type of curve, but the products that are being produced are going to be a little bit more complicated, and the process is going to be a little bit different. Right. During this entire process, the pore solution chemistry is going to be changing. All right, so the things that are leaving the surface of the cement particle and going into the water, right, the chemistry of that water is going to change. You're going to get some potassium ions, you're going to get hydroxyl ions, calcium ions, right, and what you're going to notice is that they start to change dramatically, and they change dramatically really dependent upon the extent of reaction that's really taking place. So you'll notice that there are really big changes that are taking place between, let's say, during 8 to 24 hours. And this is really where we see that rapid reaction. We're in that stage 3 of the hydration. Lots of material reacting, lots of changes taking place, and the pore solution changing considerably. All right, so a little bit in summary. All right, C3S, C2S, C3A, all right, these are the main things that we're dealing with. Our C3A is going to be very fast reacting. Our C2S and our C3S are going to be slower. The C2S, all right, is going to be the slowest of all of them that's reacting, all right, but the calcium silicates are going to give us the highest strength in the overall system. Gypsum, you'll remember, is being added, and the gypsum is really there to counteract the rapid reaction that the C3A undergoes. Cement fineness is going to play an important role in what we're talking about. The finer the cement is, the faster it's typically going to react. The mill certificate is information that's going to be provided to the producer or the contractor. Right? This is an important thing to be checking if you're trying to trace down what problems might be. It's an important quality control process to be keeping this material, to be making you alert or aware if something else may be happening. We talked about 3 methods that are out there to measure the hydration. All right, we can measure the heat that's liberated, measure the extent of reaction that's taking place. We can measure the extent of the reacted material. This could be either the water that's being consumed in terms of non-evaporable water, or it can be in terms of the amount of cement that's being used up if we're doing some sort of an image analysis. And the third one is the volume reduction, or the measure of chemical shrinkage. We talked a little bit about the 3 main reaction equations. We talked about our calcium silicates reacting with water to form CSH, and our calcium hydroxide. And we talked about the C3A reacting with gypsum and water to form ettringite. At the end of today, I will post the first homework. You'll have a week from the time that homework is assigned to turn it in. All right, so that'll be available on the website this evening. Okay? Have a good weekend. All right, any questions?
Yeah, you mentioned that CH was a